Hello gentlemen, so welcome back to a video tutorial. We're going to be talking a little more in depth about stoichiometry. So I want to give you a little more focused definition of what stoichiometry is. It's the study of quantitative measurements between the amount of reactants used and the products formed in a chemical reaction. And this is still based on the law of the conservation of mass, which states that matter can neither be created or destroyed. Now, one really important concept to remember as we go through this lesson is that in a chemical reaction, the relationship between your reactants and products derive from a balanced chemical equation. So a balanced chemical equation is your basis of all of your relationships. Remember that. For example, if I had a reaction that was between magnesium metal and oxygen gas, I would form magnesium oxide. Now, you guys know how to write this. If I wrote this out, it would be solid magnesium reacting with oxygen gas, which is diatomic, producing magnesium oxide. If I balanced it, I'd have 2 here as my coefficient, 1 here as my coefficient, and 2 as my coefficient in front of magnesium oxide. Now, another way of stating this is that I could say I have 2 atoms of magnesium reacting with 1 molecule of oxygen gas, creating 2 formula units of magnesium oxide. I'm simply taking my coefficients and articulating them in a different manner based on what I have here. Magnesium is an element when it's by itself. Oxygen is a molecule, as a diatomic molecule here is O2. And magnesium oxide, since it's ionic, it is a formula unit. I'm just taking my coefficients here and applying them to whatever I'm talking about, atoms, molecules, or formula units. Now, I can take that even further down here and say, with the same equation, that this means I have 2 moles of magnesium reacting with 1 mole of oxygen gas, creating or producing 2 moles of magnesium oxide. This is going to prove to be the most important thing that we look at for this section. The relationship that they have in moles. I can also take it further and say, well, I know that the molar mass means, the mass of 1 mole of a substance. So magnesium, if I had 1 mole of it, I would look at the periodic table and take that average atomic mass, and that would be 1 mole of magnesium. But here I have 2 moles of magnesium, so it's the atomic mass times 2, which gives us 48.61 grams, plus, or reacting with, 1 mole of oxygen gas. So I look at oxygen up there, it's 15.9994 grams per mole as its average atomic mass. I have O2 here, so I multiply that times 2, and I get 31.988 grams of oxygen gas. That creates 2 moles of magnesium oxide, which is the same as saying 80.6088 grams of magnesium oxide. I take those average atomic masses of magnesium and oxygen, add them together, and I get that. If you add up both sides, you see that they are the same, and that means mass has been conserved. Now, how do we use this? Let's go through a practice sample and actually go through how to use this. Now, stick with me. Don't start reading ahead and get confused. Stick with me in a general process. So say we have this equation, this reaction. C3H8, which is propane, reacts with oxygen gas to create carbon dioxide and water. This is a combustion reaction. When you fire up your grill, this is what happens. So if I balance this equation, I'll do it quickly. I'd get those coefficients. If you want to verify it on your own time, go for it. But I get those coefficients. Now, what this is saying, if I go back to that old slide that we just finished, I can talk about it in terms of moles. It says that 1 mole of propane reacts with 5 moles of oxygen gas to create 3 moles of carbon dioxide and 4 moles of water. Now, that is a balanced chemical equation. That's what it's saying. It's saying that when these combine and react, the ratios that they combine in is 1, 5, 3 to 4. Now, in a perfect world, or in an ordinary laboratory setting, you don't always start out with 1 mole of propane. Or you might not always have 5 moles of oxygen gas available. So you know how much gas that could be. 5 moles of oxygen gas, you can convert that to grams and determine how much that is on your own time. But say I don't have that much. Say I have less than 5 moles. Say I had only 3 moles of oxygen available. And I wanted to know, well, if I had 3 moles of oxygen gas and not 5, how much propane would react with it? It's not going to be 1. It's going to be less than 1 because I don't have 5. I have 3. So let's go through the math in that problem. So if I have 3 moles of oxygen gas, and I want to know how many moles of propane will I need to react with that 3 moles. I start off with what's given to me. 3 moles of oxygen gas. And I put it in my dimensional analysis brackets. Put that a little higher. And now I want to go from moles to moles. These coefficients are symbolic of our moles. This means 1 mole of propane to 5 moles of oxygen gas. When I compare 2 different substances, I have to compare them using the coefficients in front. They're moles. Not grams to grams, but moles to moles. That's called the mole ratio. This is what I mean. When I want to compare oxygen gas to propane, I use the mole ratio, which is the relationship between the amount of moles of one and the amount of moles of the other. So, I have 3 moles of oxygen gas here. I'm going to compare moles of oxygen gas and moles of propane gas from my chemical equation. I'll say, well, for every 5 moles of oxygen gas, I want moles of oxygen gas in the bottom so it cancels out just like any dimensional analysis problem. It's going to take 1 mole of propane. My moles of oxygen gas cancel, and moles of propane is what I was going for here. I solve 3 times 1, which is 3, divided by 5 gives me 0.6 moles of propane. So if I started out with 3 moles of oxygen gas, it would react with 0.6 moles of propane. That's the same ratio as 5 to 1. But if you don't start out with 5, you're not going to quite react with 1. Now let's do a different example. I can compare things in my reactant side to things in my product side as well. So say I have 3 moles of oxygen gas again, but I want to know, well, how much water will that produce at the end of my reaction? So I start out with 3 moles again, and I'm going to go a little faster. 3 moles of oxygen gas, and I put it in my brackets here and say, well, how much water will I make in moles? I compare 2 different substances, oxygen, gas, to water, using their mole relationships, mole to mole. The coefficients in front of them are their mole relationships, their mole ratios. So, I want to get rid of moles of oxygen gas. Thus, I say, well, same thing, for every 5 moles of oxygen gas that I have, I'm going to create 4 moles of water. So what I'm going to goes on top, as always. So I'm finally at 4 moles of water. I know my moles of O2 cancel. So I'm left with 3 times 4, which is 12, divided by 5, which I believe is around 2.1, 2.4. 2.4 moles of H2O. So if I start out with 3 moles of O2, I'm going to produce 2.4 moles of O2. In my equation, in a perfect system, if I started out with 5 moles of O2, I'd create 4. But if I don't start out with that, then I can calculate how much I would create. That's mole to moles. This is called a mole ratio. Very important, know it. Now, say I'm given moles of one thing, but I'm asked, well, how many grams is that? Because in chemistry, that's what we really measure in grams or milliliters. But in this case, grams. So I can also convert between moles to mass. Well, from moles to mass. Let's go through a sample calculation there. Say I started out with 7 moles of my propane gas, and I want to know, well, how many grams of water is that? Excuse me. So I start out with 7 moles of propane gas. Put it in my brackets. And, well, what relates moles and grams? It's the molar mass, you're right. But when I have one substance and something completely different from it, which is water, there's no direct correlation. I can't go from one directly to the other using molar mass. So I have to go from moles of propane to moles of H2O and then to grams of H2O. I go from moles of propane to moles of H2O the same way I did here, moles to moles, using the mole ratio between the two. The mole ratio between the two is 1 to 4. So you go from moles to moles using mole ratio. I go from moles of H2O to grams of H2O, we're doing what we've always done, using the molar mass of H2O. Let's try that out. So I have 7 moles of propane. I want to go from moles of propane to moles of H2O. I do so using the molar mass, doing the same thing I did up here. So I know that for moles of propane, then the moles of propane down here. Now look at my equation for this. My equation says for every 1 mole of propane I have, I'll create 4 moles of oxygen. So for every 1 mole of propane, I'll create 4 moles of water. Excuse me, I said oxygen before. Moles of propane cancel out. I have moles of water. That's what I wanted here. But I don't want to stop there. I want to know, well, how many grams is that? Not how many moles, but how many grams. Thus, I keep my dimensional analysis going, and I use the molar mass of water, which says that for every 1 mole of water, I'll have approximately 18.015 some odd grams in that 1 mole. So the exact number is 18.01528. I'll have 18.01528 grams of H2O for every 1 mole of H2O. I got this value here from the periodic table, taking the mass of 2 hydrogen atoms and an oxygen atom, and that's their molar mass. Now my moles of water cancel out, and I finally have grams of H2O, and that's what I was looking for, grams of H2O. Thus, I can solve. If I have 7 moles times 4, sorry, not 7 moles, that moles is canceled out, 7 times 4 times 18.01528 grams of H2O divided by 1 here at the bottom. What I get from that is approximately 504 grams of H2O. If I started out with 7 moles of propane, which is a lot of propane, I would create 504 grams of H2O. It's about a half a kilogram. It's heavy.